we go on to something different. I'll give an example at the end here when we're done.
So
Yeah,
Neil, when
yeah.
you look at this, I mean, it seems like a very nice solution, but isn't there some concern that we might be overfitting this data? I mean, it seems to want to really take care of all the points as much as it can.
Yeah, I mean, there's certainly a concern of overfitting here. I would, for sure. I mean, it's of course this is a toy example here. If you have like
Sure, sure.
thousands and thousands of points, you'll probably stop your process before you've classified all of them correctly.
But is there a natural concept of regularization here, or?
No, not really, not really. That's what we'll get to in the next boosting algorithm. That's actually much better than this. But,
Okay, okay.
but
Also, there's nothing like cross validation here, where you know.
no, there are really no parameters, no hyperparameters to optimize here.
Okay.
So it's all so the whole thing is kind of, I mean, the algorithm just produces this one classifier.
Can someone use like the number of classifier as a function of the number of data points that the number?
Well, you can limit how far you want the process to go, right? You can say, oh, I only want to look at 10 classifiers. I only want to do this in 10 steps here. So then you would not fit it completely to the probably not fit it completely to the data set. If your data set is large enough, and you limit the number of steps you want to take, you can to some extent avoid overfitting. But there's no direct way of really doing. You would have to try how many steps you want to. You take a validation set and try to see how many steps you should take.
I'd like to, say first of all, in practice, gradient boosting in all its variants is much less subject to overfitting than things like trees. It really doesn't. The other thing is, if it would make it impossible to do an example like this, but you could the two parameters that come naturally is Niels just did stumps, but you could do more depth to the trees. And also you could add a learning rate to how much of each new classifier you throw in. So those.
Yeah, I mean, if you do trees that have more branches, then you probably overfit worse, I would think. So
typically stumps work really well, but there are times when you don't want to have really deep trees, but 2 or 3 or 4 or 5 sometimes can be better. But also the learning rate becomes important. That's been my experience when I've done them anyway.
Okay, yeah, well, I mean, ADA boost is not it's not the state of the art, that's for sure. But the state of the art is gradient boosting that we'll see now. That is the state of the art. And that's both much more general, and you can also regularize it so to avoid overfitting. So again, let's look at a data set. And again, so we have labels for each data point. And suppose we have some classifier. Again,
just before we move away from AdaBoost. So clearly there was some excitement about AdaBoost.
Yeah.
Did they just truncate at some stage of iteration? Was that their prescription they used?
I don't know. I mean, I don't know what I mean, there certainly was a lot of excitement about it, I guess, but it was before I got into it, so I wasn't part of the excitement.
But it seems like the only thing they could have done was to kind of somehow get a feeling for when they can cut off the
yeah, for sure. Yeah, right.
So I can add some history. I've read a little bit about this. Actually, when it originally came about, people thought that this was a method that was completely resistant to overfitting. And it wasn't until years later that they came up with examples where that you could show overfitting occurred. So it is somewhat resistant to overfitting, but That's the history for overfitting.
Yeah,
people were excited because they said,
probably less prone. Yeah, I mean, it's probably less prone to overfitting than say like bagging or random forest.
Yeah,
So
typically.
because you are using these very simple tree stumps. So you can see you sort of get more regular decision boundaries here. You're not going to get some. I mean, if you use random forest, you get weird. You can get very weird decision boundaries, which tends to be a sign of overfitting.
But Niels, the only reason why maybe I'm reasoning wrongly, but the only reason why I look at this and think of overfitting is because if we run this iteratively, it seems like you get every point classified correctly, right? Eventually.
Only because this example is so.
I don't think so. I don't think there's any theorem that says that you. I mean, if you go to infinity, you will, but I'm not sure.
Yeah, that's what I was extrapolating.
I mean, it'll converge to something that fits everything. But I mean, just because it fits the data set perfectly, that doesn't mean that it necessarily overfits.
No, but it seems to. The intuition is that when you have a decision boundary that's so finely tuned to the data that's given to it, to the degree of getting every point classified correctly, it seems very, very much attuned to the data.
I mean, this is only because it's a very small example here. But if you have like hundreds of thousands or millions of points, right? Then you would not. I mean, you wouldn't take a ADA boost with that many steps in it that you would fit all the points correctly.
Okay.
So you would stop at some point of time, but again, it would depend on a validation set, how far you would want to go. I mean, you would want to optimize in such a way that you get the best possible score on your validation set.
Sure.
So yeah. Okay. The gradient boosting, that's really very successful. That's a really good boosting algorithm, and that has actually proven itself to be pretty good at a number of these competitions that goes on at this website Kaggle. So the idea here is again sort of a stepwise construct and classifiers here. So again, a classifier here, it can be it's a function, so it can be a linear function or it can be some other function. And so let me assume I have some loss function, and that could be anything. I'm not talking about just the exponential loss function or the cross entropy loss function. It could be any loss function here. And so the loss function is the average of the loss at each point. So at each data point, my classifier gives me a value here. The loss function measures, is this far away from the actual value that I wanted to, or is it close to? So this is what a loss function does. And the loss function over the whole data set is the average of these local loss functions. Now I put a minus in front of it here to minimize these. So then I want to look at another classifier. Suppose I take a function g and add it to my classifier f. Of course, I want to do it in such a way that I improve my loss function. So if I take the loss of my new classifier f plus g, I want that to be better, and that means smaller than the loss I got from the previous one. So I want to try to add some function here in such a way that I improve the loss function and make it smaller. So the way I'm going to do this is going to look at the values on my function here on each of the data points. Let me call that zi. So that's a number. So if I do that, then I can you see the only thing that appears in the loss function are the values of this f on the data points. I don't need to know the values of f on every point. I just need to know it on the data point. So let me give those values on the data points. Let me give them names z1, z2 up to zn. And then I can differentiate with respect to these variables. I can take my loss function and I can differentiate with respect to these. And that of course is very, very simple, because the loss function is a sum of function, and each of these functions only depend on one of the parameters. So this would be ci here, right? So it's a sum of functions, and each of them only depend on one parameter here. So if I take my loss function, differentiate with respect to zi here, well, all the ones that are different from zi here are going to disappear because they don't depend on zi, and all I'm end up with is this
one
number.
term.
Yeah, one term. Exactly. So let's just try an example here and see how this works. So here I'm looking at the logistic loss function, and I have just a simple data point. So I have some classifier. I don't know what it is. This just some classifier f, and I look at the loss function here, and so it's minus log of the of this probability, which is given by the logistic function. So this little loss function here is given by this. And well, I call this f, the value of f at this x, I call that z. There's just one c here, so I don't bother putting an index. So my loss function here is a function of z is given by this. Well, log of this is minus log of the denominator. And again, if we were doing logistic regression, then our f would be of this form. It would be just some linear function. It will just be a vector, fixed vector dot x. But we're going to allow f to be some more general function here. We're not restricting ourselves to just a linear function. So the probability of the label being 1 given the data point x is, well, that's the logistic function here, x of minus z, because here now y is equal to 1. And then the probability that it's minus 1, well, that's 1 minus the probability that's equal to 1. And if you compute this, you get 1 divided by 1 plus x of z. So the two probabilities are 1 divided by 1 plus x of minus z, and 1 divided by 1 plus x of plus z. So the probability in any case is given by this. It's 1 over 1 plus x of minus y times z. Take the derivative of this with respect to z. We get this expression here, which we can also write as this if we want. We don't necessarily want to do that, but of course, you can simplify this just by dividing through by x to minus yc. Then it gets a little nicer. So we get the gradient. So this is, if I divide through by the numerator here, I get a 1, and then I get x of yz plus 1. So if I take the gradient now, if I have a data set, so more than one data vector, then the gradient of the loss function, so that's the vector of the derivatives with respect to each of the z's, so that will look like this. This should be y2, ym sub 2 here. So that gives me the gradient. Now I want to use Newton's step here. I want to use a Newton descent sequence. So what do I have to do? I have to compute the Hessian, meaning I have to compute the double derivatives. But again, this is not very difficult because there aren't any cross derivatives here. Because if I take the derivative of L, or the loss function with respect to Cj here,
vanishes.
No, it doesn't vanish, but it just gives me something that only depends on Cj, right? Because it just, yeah, it kicks out all the terms except one.
Only the diagonal terms. Sir.
Exactly right. So if I take the derivative of this here with respect to one of the other variables, I'm going to get 0. So all the cross derivatives are going to be 0, and so the Hessian is just going to be a diagonal matrix. And so it's just going to be the double derivatives with respect to the CIs. That's going to be the ones in the diagonal. You can probably figure that out, what that derivative is, and we get this expression here. So,
Niels, if I can ask, maybe I'm confusing myself, but it seems like we had a kind of smooth function originally to start off, but then we did this clever trick of just taking the endpoint support of that function.
Yeah.
Right? And then we kind of did a gradient descent in this n-dimensional space.
Well, not yet, but we're going to.
Yeah, you're going to.
Yeah.
Why is it? We are still minimizing that function, but somehow this seems more doable than actually trying to minimize the function. What happened here? I mean, is this?
I mean, you're going. I mean, the thing is that we're going to take a step where we make the where we make the loss function smaller, right?
Yes. Yes.
And what we're going to do is we're going to take that step, and we're going to approximate that by a function.
Yes.
So that when we if our function is actually equal to the step we're taking, right? Then we have the new function will be f plus the step, and that will make the loss function smaller.
Yes.
So the idea is to as we will see to take this Newton step and express this as a function, a values of a function.
Right, because Niels, if I understand correctly, like it's the same thing which we did in logistic regression. We are using Newton's method to do it, which is like gradient.
Yeah, that's right. Except there we were actually we were taking derivatives with respect to something else.
Right.
Yeah.
Because there the C1s here were W dot XI, and then we were taking derivative with respect to W. Right here we're just taking derivative with respect to the whole thing with respect to, so zi here is W times xi.
Yeah, so Manish, it's kind of like a sleight of hand, right? In the other case, we were moving down, like if you take a two-dimensional example, we were moving down a well to find a minimum. But here we replace that smooth function with endpoints.
Yeah, because the loss function only depends on the values at these points. It doesn't depend on anything else.
Correct. So, yeah, it's very cool. I mean, the math simplifies in this case. Yeah.
It's very simple. But anyway, so in our logistic function, so the cross entropy loss here, we're getting the diagonal of the Hessian just has these terms in it.
Yeah.
So then the Newton step, how do we take the Newton step? Well, we take minus the inverse Hessian and multiply that onto the gradient. So we have the these are diagonal terms in the Hessian. So the inverse Hessian, well, that's just the inverses in the diagonal. So here we have the we had minuses. We had actually minuses in front here. Yeah, we had minuses here. So the Newton step here becomes this matrix probably here, this diagonal matrix times this. And if I compute this out, I get this, this vector here. So then the idea is that I have these values here, and if I add these values to my z's here, then I'm going to lower the loss function, because that's what the Newton step does. It lowers it converges to the minimum of the loss function. So I'm going to lower the value of the loss function here. Now these are just numbers here. This is they're capital N numbers here. So I don't have a function yet, but that's my next step. So I want to find a function g such that its value on the data points are precisely these numbers here, or at least very close to it. So if I have such a function, then I can take my new classifier f plus g, and that will actually improve the fit. That'll lower the value of the lower the loss function.
So basically, by discretizing it, you don't have a function. You have endpoints, and now you're saying I'll
right. Now I want to find a function
that fits kind of.
Yeah. Right. And so how do I find such a function? Well, that's where we're going to use what we talked about earlier, a regression tree. So, but there's now we have done this for the cross entropy. So when we have a binary problem, but you can see it's very easy to do in general, because the Hessian will always be diagonal. It doesn't matter what loss function you take, as long as you have a loss function that's a sum over over these local loss, or the loss at each data point, then you'll always have this situation. The Hessian is a diagonal matrix. So it's not going to be, it's going to be pretty easy to do this in general, for a general loss function. So so we want to find this function, and so we're going to use a regression tree. And the regression tree, as we talked about, is very similar to the decision tree. So except we have we don't have labels. We in fact have numbers here, and so of course the numbers we have are these numbers here. We want to find a function that at xi gives us this value here. So again, to fit a regression tree to so this our data set here would be the original data point, and the yi's would now be these numbers here. So again, we use an iterative process. We try to split to optimize some measure of impurity, and so, but in this case we're using we split. Suppose if we split at some coordinate xk here, and we're splitting and look at the points where the kth coordinate is less than s, and look at those where it's bigger than s. Then we want to optimize an expression of this form here: c1 minus yj squared plus c2 minus yj squared, will be sum over the two different the two data sets were split into. These values c1 and c2, where we want to find the value c1 and c2 that minimizes this expression here. And this is, to find this, you can just differentiate with respect to c1, and then you get the fact that c1 must be the average of the y's in this data set, and the same for c2. Has to be the average of these y's in this subset here. So we just have to again look over all the splits and compute these values here, and find the one that find a split that makes this number here the smallest. So that's how we decide whether we're going to split or not. So if we split then we get minimal. Yeah, so this is just what I said here. So nothing special about this. So the function associated. So we can construct a tree this way, and we can go down the tree as far as we think is appropriate. And a tree then gives us a function, right? Because we can take a point and we can go through all the rules and see where the point ends up in the tree, which leaf it ends up in, and we then define the value at that point to be the average of the y's, the different y's that are at this leaf. So they may, if it's pure, then there's only one y, and then that's the value. If there are more than one y, then we take the average. So that's how we take this tree and turn it into a function, and that will in fact be a locally constant function. So here's a little example of it. We have just so it's just one-dimensional data. We have 3 data points: 1.0, 2.0, and 3.0. The y's are 1.5 and 1.0 and minus 0.5. And so here's my tree. It's a tree stump. I split at x less than a half, less than 2, sorry. And that gives me this leaf here. So that means that when x is less than 2, the function takes a value 1.5. When x is bigger than or equal to 2, then I have these 2 points here in my leaf, and I take the average. So that's 1 and minus half divided by 2. That's half divided by 2, 0.25. So that's the value of the function here at when x is bigger than 2. So it's just a, yeah.
This seems like it's a beautiful example because it shows everything very clearly.
Mm-hmm.
The only question I have is why was it just illustrative, or is there a reason why we choose? How do we choose x less than 2 to be the place to split?
No, this is just my example to show how we get a locally.
So you're saying there's always a way.
Constant function.
Okay.
It'll always be a piecewise constant function.
Yeah.
From a tree, right? That's what I'm trying to show here. So.
Yes.
So this has nothing to do with the previous, but it's just to show that the function we get from a tree will be piecewise constant.
Yes. Yes. And you're saying that this will always be the case given any tree. If you pick a node and split at that node, right, you're always going to have a left-hand side and a right-hand side, and the average. I mean, average on the left and the right. Yeah.
Right. Yeah. That's how you, yeah. And so again, you have to decide how far you want to go. We start. So here's how the gradient boosting algorithm works without the regularization. We'll get to the regularization later on. So we start with a constant function. We take a constant function and we choose this constant function to minimize the loss function. So that means we're not looking at any sort of classifier. We're just looking at a constant function a. We plug that in, and we can differentiate with the loss function with respect to that, and we find the one that minimizes the loss function. So then that's our first. That's our F0. Then we do the Newton step as we saw before, and we construct, we find these n values, and we fit a tree, a regression tree to this, and that gives us our new function. So that's a plus t0. F1 is a plus t0, and we can continue this way until we are happy with the way it fits. And after m steps, our classifier is the sum of these tree functions. They start with the constant ones, and then we have add these trees to again, this is a piecewise constant function. So let's see how we do that in our example here. So we the same example we did with the ADA boost. So let's see if we can go back to that. So we had these points here, and let's try to apply this to apply the algorithm to these points here. So so there are 8 points, and let's go back and see what we have to do. So we're going to use the cross entropy function here. So that's for a function f, or for a classifier f, the cross entropy loss will be given by this. There are 8 points. Each of them is log of the sigmoid function, or the logistic function. It's given by this, and if you want to find out which constant function minimizes this expression here, so what constant function should we choose here? It turns out if we figure that out, we get that it's just a constant function, identically 0. So if we use our formula for the Newton step we had here, there was this thing here. We can see that z1 up to zn, well, that's the values of the constant function we started with. They're all 0. So the Newton step here, well, these are all the z's are all 0, so it's 2 times the label, and the labels were plus and minus 1, right? So we simply get that the Newton step is given by this. So we have to construct a regression tree that fits these values here. And so if we do this, I take the tree with the split at, so this of course depends on the training data, or the data set we had, but I split that at x1 equal to 0, and I split it at x2 equal to 2.5. And if I fit this tree to the Newton step, that gives me a tree function like this. It's minus 1/2 if x1 is less than or equal to 0, and it's minus 1/2 if x1 is bigger than 0 and x2 is less than or equal to, and that's given by this. So the tree is this tree here. So that gives me, that's my regression tree. That gives me the function, and this function actually perfectly fits the data set. So that separates the data set. So that gives me this decision boundary here. So this is all well and good, but what about regularization? Because that we can put into
that was just, so basically in this case just one step was enough, right?
Yeah, one step was enough, right? Yeah. Right. So this is just a tree that separates this. So in general, if we have again computed our classifier like this, then again we do the same. and we want to find the function that does the best job of improving the loss function. And again, the values, the z's are going to be dependent on the previous function, because that's going to be, the z's are going to be the values of this function here on the data points. And so that's I mean, one can figure that out, how this works. I mean, you use the quadratic Taylor expansion in these parameters, and then again is again very, very simple, because each of the loss function is just the sum of these terms here, and each of them only depend on one variable. So it's very, very simple. We can just expand the individual terms. So if we expand look at Ci plus this Fm at Xi, we get approximate quadratic Taylor expansion like this, and we can give it names. We define G sub I to be the derivative, and we define H sub I to be the double derivative, and Wi to be the value of this function Fm at Xi, and so we get that the value of this term at Zi plus the increment is basically given by this, or close, is close to this expression here. We're approximating by quadratic function. And so again, we can find the one that gives us the best or lowest or minimizes this. We can find the Wi that minimizes this function here. That's the value of the function we want. So that's the value of that's the value we want. And if you do this, you minimize this quadratic function, you get that Wi is given by this, and the minimum value is given by this. So we basically we lower the loss function by taking Wi to be equal to this. So that's just the same as what we did when we were talking about the Newton step. The Newton step is simply by replacing the function by a quadratic approximation, then try to find the minimum of that quadratic function and keep doing that. So we should then try to fit a tree, a Tm, to these W's. So that would be, that's the thing that we have to do. We could do that using the regression tree method. So splitting at the coordinates that gives us the best impurity. So the lowest the impurity the most. So to do regularization on this, we can regularize in different ways, and we can regularize not just well, what do? We want to limit the size of the W's, but we can also limit the size of the tree. So if we define the regularized loss function here, it's given by the sum of the sum over the data points here, and then we add two regularization terms. We add the lambda regularization constant times the square of the Wi's plus, and then we add this regularization term here, which is a term that regularizes the size of the tree. So we put in the size of the tree we define by the number of leaves, and so we want to minimize this function here, but now gamma now it depends on the size of the tree. So if the size of the tree grows too much, then we won't be lowering, we won't be minimizing, we won't make the loss function smaller, because maybe the tree will grow so much that it makes up for our for the using the Newton step to lowering the loss function. So here again, the two hyperparameters, the gamma, the regularization constant for the tree size, and lambda for the size of the W's. And so if we put this in here, we get the new W's here. I can do this by again, just to my quadratic approximation, I'm just adding this term here, and that's going to give me a new WIs that are given by this. So so let's assume that we have given these WIs given by some tree. So each WI is a value at some leaf, and so let's look at a leaf in that tree, and let's look at the data that lies in this leaf. So that's what, after splitting the data set a number of times, we end up with these. Then we have to figure out whether we're going to split further at this node here. So the regularized loss function is going to look something like this. So the quadratic approximation is going to look something like this, and so it's just the value here plus, and then this quadratic function here, and plus the regularization term that comes from the tree. And I can rewrite this in this way here, so that's not so special. So if we look at the loss function that comes from this leaf here, so that means we're just going to sum over the data points that lie in the leaf, and let's say that this is W star sub n here. So n is the particular leaf we're looking at, and so W star n will be given by this thing here, and the optimal value is then given by this expression here. So the improvements in our loss function we get by adding this function, which is defined by the tree with these nodes. Well, that's given by this thing here. We're subtracting this term here. That makes a loss function smaller, but then we have this regularization term from the tree. And so what's the difference? What happens if we decide to split at this leaf? So suppose we want to say, okay, I'm going to try to split at this leaf I have here. So I'm going to so that, what does that mean? That means I'm going to lower my loss function further, but I'm also going to increase the size of my tree. And so if we try to figure out what happens if we split the tree, what do? We split it into two new leaves, a leaf left and a leaf right, and that means we're going to get we're adding one more leaf to the tree. So what we're going to get then is the new terms we subtract. Then we had the term we had from before. So this is the improvements we get here. These will be when we subtract them, we'll get a better loss function. But then we add the gamma here. So the question is, adding the gamma, is that going to make this number here positive or negative? If it's positive, then we're actually not going to lower the regularized loss function, and so we wouldn't split there. We would leave the tree in this as it is there. If it's negative, well, then we can split there and still improve the regularized loss function. So we're using this to find the best split at a given leaf. If we might not split depending on what this number here is. And this is how we will sort of decide whether to how much we want to refine the tree, how many splits we want to have in the tree. And so that is how the gradient boosting algorithm with regularization works. It will prevent us from making trees that are too big, and also it'll limit the usual L2 regularization. But that's the state of the art. Let's just quickly run a little example here. So I tried to apply this to our data sets here. Is this on the screen now, the code here? Is the code on the screen?
No.
Or what?
No, Niels, we have your PowerPoint.
Yeah.
Oh, okay, so I'll have to find the other one. Hold on. There, now you should have it, right?
Yep, it's there.
Okay. So it's a yeah. So just some standard imports. Hopefully, there we are. And then this credit set that we have seen before. I download that, and here's some of the points. I don't want to take the client ID, so again I take the first columns 1 up to 4. I make so here the labels are 0 and 1s. I make them -1s and 1s. I split it into a train set and a test set, and just to see how many I have of -1s and 1s, I can look at. I have this thing called a counter, which will count how many there are of each, and I just want to look at the fraction of plus and -1s in the training set and the test set. So I get something that's pretty similar. I scale them, though I really don't have to scale them for a tree based method. You really don't have to scale it, but I did it anyway. So let's first look at the AdaBoost classifier. So the AdaBoost classifier is in the sklearn ensemble, and I can download it, and it gives me a warning. And so instantiate. So I'm not going to bother with setting any parameters here, but you can set parameters here. So fit it to the training set, and you can see there are a number of things you can set. There's a number of estimators you can set, and the learning rate. Let's see how well it predicts on the test set. And let me look at the accuracy score from the test set. And my God, it aces the test set. So it's trained on the training set, but it correctly predicts everything correctly on the test set. So the gradient boosting classifier is not really in sklearn, but I'm using one that's called LightGBM, which is made by Microsoft, and it's very fast, so I like that. But there's another one, XGBoost, which Adam likes. Is that right, Adam? Because I think that, I don't know, maybe light TBM.
Yes, I like that.
Maybe light TBM.
I have nothing against XGBoost. I mean, against light boost, but you know, these things can get pretty complicated, and until somebody shows me that light boost is significantly faster all the time I put into XGBoost, I'm going to keep it.
Maybe light TBM doesn't work on R. I don't know. So, but light TBM is actually it's supposed to be extremely fast because it uses some. But let's see how it again. We instantiate a gradient boosting classifier. Again, I'm not going to set any of the parameters, but I could set both the hyperparameters. That you do have a gradient boost in sklearn, but it's not very good because you can't set hyperparameter. It doesn't have regularization. So let's see how that performs. We fit it on the training set, and we can see here that has a number of different things here that you can set. Also, there's some warnings here. I don't know why they don't update it, but anyway. So let's see how well that does on the test set. And that also aces it. We can see the confusion matrix is perfect. And so this is not on the training set. This is on an independent test set. So it trains on the training set, but it also is. I mean, we haven't looked at how well it performs on the training set, but it probably doesn't do too much worse than on the test set. So it aces the test set, 100% correct on the test set. So the gradient boosting algorithm, even though it's not a deep learning thing, it works very, very well in practice. So it's a very good classifier. All right, so there was boosting, and I guess Adam will then apply these some of these things next time to a real live data set, and we'll see how it works in a bigger scale than this. All right, are there questions about it? So there's quite a bit of math in this, I have to say, but hopefully you can sort of figure out what the idea is very simple in the sense that you want to take this Newton step, and you want to approximate this vector of the values with a tree, the function coming from a tree, and you keep doing. Questions? Okay.
Right. Thank you, Niels. Tejas, do you have anything?
Yeah. No. I was going to say, Niels, that it really it probably needs little time playing with the math. Is not complicated. It's more like bookkeeping, right? Because everything falls into some very clean pieces that can be aggregated in a nice way.
Yeah, I mean it's fitting the trees that there you have to use the algorithm to do that. The rest of it is sort of amazingly simple in the sense that it's I mean, the idea is great that you just look at these values of this function, of this classifier as variables, and then you just try to expand in terms of these variables. So to lower the
yes. So Niels, can you make a general? I mean, I'm pushing you into general mathematics here. That I have some loss function. Mm-hmm. I sample at discrete points. I look at the derivative with respect to those points.
Right.
And then write a Newton algorithm.
Mm-hmm. Yeah.
This idea, can I use it for any kind of smooth function? Sample at some points, and then take a step, and then I have to build a new function of some kind. Is this a general thing? or is there something very special going on here?
Well, it depends on what you want to do. I mean, when you're doing it for the loss function, that's. I mean, the idea is the smaller the loss function, the value of the loss function is, the better the fit to the data is, right? So that's the.
But that seems to be a general pattern with any loss function, right? If I'm not just doing, I mean, any loss function where I have n data points.
Yeah.
It really has, I mean, we are drawing a smooth function, but really we only know its value at the specified data points, right? Unless we do some interpolation or extrapolation.
Yeah.
So,
I mean, in general, the loss function we've looked at depends on parameters. So the function f there that we're looking at, in general, is something that depends on some parameters.
Correct.
And what we're doing is we're looking at minimizing the loss function with respect to these parameters. But that's not what we're doing here. And here we're not having a parameterized function. We're just having some function, and we're trying to change this function, not by changing its parameters, but by adding another locally or piecewise constant function to it. So that's sort of all we're doing here. It's I mean, the loss function is just the only. It's not really a. I mean, it depends on the values of this classifier.
Yeah. So depending on parameters, it depends on the values of the data, right? That's kind of the twist.
Yeah, right. So it only depends on these n values.
Yes.
Unless you have a parameterized function. If your function is parameterized, then it'll be a smooth function of these parameters, and that's what we did before.
Yes.
We minimized with respect to these parameters. And that gave us the actual function that we're looking at. But here we're just starting with some function, and then we are boosting this function, and that's what it's.
With some kind of discrete stepwise point.
Yeah, right. We're improving this classifier rather than so let's say we took a linear function and we just took some parameter w and looked at that loss function. If w was just some arbitrary vector, then there wouldn't be. But we could try to do this the same thing here. We could try to boosting here, so that we would get then it wouldn't be a linear function anymore, but it would be a linear function plus some
jagged thing, right? I mean,
piecewise constant. Yeah, piecewise constant function. Yeah.
Yeah, that's just a very mesmerizing and clever idea, I think.
Yeah, it's a very clever idea. It's a beautiful idea. Very beautiful. It really. I mean, but I mean, the computation is in finding in constructing the regression trees at each step. That's where yeah.
Probably also a nice exercise would be to look at the decision boundaries in some small dimensionals, in the two-dimensional cases, for some larger number of points, and compare those decision boundaries to like a logistic classifier or something, and see what it's trying to do better, right?
Yeah, I mean it will. Yeah, I mean you can definitely do that. I mean you just take some take some two-dimensional data set and then try to some of the ones that we looked at, you can try to do gradient boosting,
and then it'll be nice to plot step by step how the refinement is happening, right? For each
that would be so you start with a constant function, right? So that's and then you build on top of that. So that's you can sort of easily write a little program that does that.
Yes.
Sure. Yep.
Okay. Thank you.
All right. Okay. Thank you, Niels.
Thanks.
Thank you, Adam. Bye.
Okay,
Bye. Bye.